Okay, good afternoon, everyone. So let's get started. So for today, we'll continue talking about efficient deep learning. So if you recall, right, so last lecture, we kind of discussed there's a couple of challenges, right, to deploy, these large-scale trained deep neural network in real-world applications, right? So for example, the first challenge was mentioned, right? So with all these different devices, with different computing resources, how can we deploy such model, right, on these IoT devices? And if you want to fine-tune a pre-trained model, right, how we can do some efficient fine-tuning, right? Because if you want to do the full fine-tuning, then there's going to be a lot of parameters you have to adjust, right? And finally, we have all different large-scale multimodal data, right? So how we can train or leverage these multimodal data to train a foundation model in an efficient manner. So for the first challenge, last lecture, how we are able to deploy some of the models on varying resource devices. We kind of touch upon the efficient neural network design, right? So we talk about we can do network pruning, right? Basically, you can reduce the number of neurons or weights in the network so that you have a smaller network that is able to, compatible with the computing resource on the edge device. So you can deploy that in the inference time. We also talk about some of the efficient network architectures, right? Like the mobile net, shuffle net, ghost net, right? So they have different efficient design principles, right? The mobile net, notably, is you have the depth-wise separable convolution and the point-wise convolution, right? Trying to reduce the number of multiplications. And we work out some of the details, right? So how these depth-separable resolution convolution is able to reduce that computation. Another way is we can also, look into the network quantization, right? So we can reduce basically not the full precision, right? So we can reduce the quantization, the bit resolution so that we are able to achieve computation and energy efficiency. And lastly, we also talk about knowledge distillation, right? So basically you have a strong teacher network, right? So this can be a very large over-parameterized network. And you train also using that to train a student network, which is lightweight, right? So hopefully the student network is trying, aim to behave like the teacher, right, during the training. Then when to the inference stage, you don't have to deploy this large teacher network, right, because the student is able to perform or achieve similar performance as a teacher. So you can just deploy a very lightweight, small student network. So that's the knowledge distillation. Of course, so these different techniques, you may be considering combine multiple of them, right? So you can do network pruning, you can do knowledge distillation, or even you can also throw in efficient architecture design so that you achieve maybe the best of all these different paradigms, right? So trying to make it more efficient. Sure. Okay. Let me. So for those still online, can you see the slides now? Okay. All right. But let's go back to check this question again, right? So here we are talking about the varying, resources, right? So you have drones, cell phones, smart cameras. Is the efficient neural network design the ultimate solution, right? It is able to solve this problem. So the next, I'm going to talk about some of the research work is being done in my group. So we are, developing these adaptive or dynamic network for image and video understanding. So we are tackling the problem that is the traditional neural network are static, right? So basically you have a specific network architecture, right? Either a CNN. For the CNN, you may have different architecture, right? So the mobile net is the efficient architecture, and you have the common like the ResNet 50, and maybe you also using the vision transformer like the VIT, right? The VITB in this kind of architecture. So each of these different architectures has specific configuration. So it's fixed, right? So the mobile net has maybe 4.2 millions of parameter. If you run this mobile net, you will have 575 millions of floating point operations. So you have all these numbers for other network. So basically, once this is trained, and when you deploy this model, it has to execute in certain requirement, right? So if you using the mobile net, you have to ensure at least you have certain GPU memory that is able to store this mobile net, right? So billions of parameters, and you have enough computation that is able to afford like 500 or around 600 millions of floating point operations. But as we mentioned earlier, right? So in the real world scenario, these computation can be very differently, right? So you have the cell phone devices, right? So IoT devices, and even on the same devices, these computation or resource can also changing, right? So let's think about you have a cell phone, right? So then when you open a single app, right? So maybe the cell phone will allocate all the memory and the computing power for you to perform certain task for this app, right? So the app could be taking a photo, right? So you can run some object detection, super resolution, trying to take a very nice, good photo. But imagine you have multiple apps open at the same time, right? So you maybe have, chat app open in the background, or maybe you also have some other, app, maybe a game open at the background. So you have multiple app running at the same time. You can imagine, the device have to share all these resources across all these different apps, right? So then the memory and the computation may not be fully focused on a particular app, right? So basically the resource budget are always changing, right? Even on the same device, right? Depending on how task has been prioritized. And also, you can also think about another application is if you are flying drone, right? So when the drone is fully charged, right? So you may able to run some heavy models, but let's say after 1 or 2 hours, your battery become low, right? Become 10 or 20%. You want to ensure the drone is able to fly back, right? So how you are able to, accommodate this kind of, resource change, right? So here, the fundamental question we want to ask is how can we cope with these kind of dynamic resource, right? Achieve a trade-off between accuracy and the efficiency at the inference. So one thing we can think about is that, okay, so all these networks are static, right? So let's say if my resource suddenly become, have a lower resource, right? So the computation memory become lower, then what I can do is, maybe I can slim the network, right? So here we are using a CNN network as an example, right? So here 1.0 means you have a full network. Let's say this is a full ResNet 50, okay? What you can do is you can reduce the number of channels, right? So for each of the layer, right? So width corresponding to the number of channels for each of the layer, comp layer. So 75% means I only keep maybe the first 15%, 70% of the channels. Okay, I just remove the last 25%. So this figure just showing an idea, right? So this is the full network, right? And the blue version, the blue area means I only keep like 70 or maybe 50%. So I get a slimmed CNN. So in this case, I can reduce the computation, right? Because I don't have many of these channels or convolution operations. So I can reduce the floating point operations. That can maybe save battery life, right? Or maybe save some of the memory consumption. But and we actually test this, right? So this is a fully trained original network, the mobile net, right? So you can see on the image net, you can have the 70.6 accuracy. But during the inference time, if you just this blindly reduce the network width without the retraining, and you can see there's significant performance drop, right? So without retraining, so the cross here, the performance dropped from 17.6% to 14%. Okay, of course, you can gain some performance back by do the retraining, right? So here, the tech means we reduce the network width to 75%, but we retrain it on the ImageNet so that it won't suffer too much. And we further do this, right, to reduce into 50%, and we do the retraining or without retraining. As you can see that without any retraining, the performance dropped, to less than 1%. So in actual applications, right, when you're flying out the drone, right, so you don't have the resource to do the retraining, right, because you flying the drone out the field, then they have to perform all kinds of tasks. You cannot do the retraining on the device. So you want your performance without retraining to be very high, which means, if I slim the network to 50% without any retraining, hopefully I still get a very decent performance, like maybe 55%, not this 0.4%, right? But at least for now, if you just reduce the network width, this is not achievable, right? Because without retraining, we suffer a lot, for the performance. So another, solution maybe we can consider is, okay, so I, may have to do some trade-off, right, between the accuracy and the efficiency. How about I just, store many possible model variants, right? So let's say I install like a ResNet 50. I consider this is the largest model I can run. I can also install MobileNet V1, right? So this, many parameters, right? Reduce parameters and the flops. And also I can even, install another one, right? The MobileNet V2 has also a reduced parameter and floating point operations. And you can even consider, right? I can prune a network into many different versions, right? So here, this is the full network. Maybe this is 80% pruned, and this is 60%. Maybe I have like 30%, 20% pruned network. So in the inference time, right, depending on my computation and the memory budget, right, I can switch among them, right? So for example, I have enough, computation memory, then I will just using the full network. When the battery running low, right, the computation memory become low, then I switch to 75 trained or pruned network, right? So you can switch among these different models. So that's like the very easy, straightforward way you can do. But you can think about this is not scalable, right? Because you have to store multiple versions of the network, right? Maybe like 10 or 15 if you want to have a very fine-grained, trade-off between efficiency and accuracy. So we want to have this also means you have to consuming, more memory or storage, right? Because you have to store like 10 or 15 models on the device. So in this case, we want to have a very scalable solution, right? So in the runtime, we are able to dynamically trade off between accuracy and efficiency. So how can we solve this problem, right? So let's look at the conventional or the vanilla convolution, right? So this is the, the C means the input channel, right? This is the output channel, right? The computation is going to be involved with this input and output dimension, and also related to the kernel size, right? K by K, and also the input size, right? How large is your input image, right? If it's a large image, then you have involve more computation, right? Because you have to slide this kernel across a large network, a large input. Usually the kernel size are fixed, right? We're using like 3x3 or 5x5 throughout the network. So basically we have these two tuning knobs, right? So one is basically related to your network size, right? How many channels for each of the convolution layer. And the other is related to the input size, right? So you can essentially reduce the computation by maybe reduce the input size, right? You can maybe downsize input so that you can reduce the computational cost. So, based on this kind of observation, right? So we want to leverage these kind of tuning knobs, right? How we can achieve a good trade-off, right, between network width and the input resolution to have accuracy efficient trade-off with a single network. Okay, so here our goal is not install multiple networks, but just using a single network. And during inference time, we can switch or maybe changing the network width and also input resolution to dynamically adjust or fit the computation budget. Okay. So in this case, we develop this method called mutual net. Okay, and this is how mutual net training looks like. Okay, so here this is just a very this is the usual training paradigm, right? So you have an input resolution, and you have the full network, right? Let's say we're using a mobile net V1 network, right? So you train this using ground truth labels and using cross entropy, and you train the network, right? So this is the standard network training. But to achieve our goal, right? So we want to have a network that is able to kind of dynamically change the network architecture to achieve this efficiency and accuracy trade-off. What we do is, besides this full network training, okay, we also have a couple of subnetworks. So basically, you have a bunch of subnetworks. Okay, how do we generate the subnetworks? So we basically kind of slim the network width, right? So the number of channels to keep in each of the conv layer. Okay, so we can specify a specific lower bound. Okay, let's say my lower bound or smallest subnetwork will have 25% of the channels in each of the layer. Okay, then the upper bound is the full network, like 100%, right? And in between, I can randomly sample the network width, right? Maybe this will be 70% or 80% or 60%. Okay, so basically you have these random width subnetwork. And also we talk about, right, another trade-off dimension is we look at different input resolution, right? Because that also affect the computational cost. So in this case, we can also input varying input resolutions. So we have the original resolution, and we also have a bunch of downscaled copies, right? 192, or maybe this is 128, right? And for these different subnetworks, the small subnetworks, each will have a chance to take any of the resolutions, right? Maybe in this training epoch, this subnetwork was taking a 192 resolution. Maybe in the next training epoch, okay, this subnetwork may be taking another resolution, which is 128. Okay, so here we have the full network and all these subnetworks kind of trained together. So one thing to note is that these network weights are shared across the full network and the subnetwork. Okay, so basically their weights are shared. They don't have like separate weights. So all the weights are shared. They optimize together. And for the full network, we have the cross entropy loss. Okay, we consider this is like a teacher network, right? Because it's always using the full resolution, always using the full network, and using the ground truth due to the cross entropy loss. For the subnetwork, right, we consider this is like a student network, right? Because they have like smaller network width, and they may using a smaller version of the input resolution, and we're using the KR divergence as the loss function. So basically, taking the teachers or the full network prediction logics and measure the KR divergence, right? We talk about in the knowledge distillation part, last lecture, right? So the KR divergence measures how different two distribution is. So we want to minimize the KR divergence, right? So the subnetwork trying to predict the logit similar or close to the full network. So in this case, we'll have a bunch of loss terms summed together, right? So we have the full network loss, cross entropy. We also have these subnetwork loss. So in this particular example, right, so we have 3 subnetworks. So we sum them together. Okay, so they all have like KR divergence loss.
Professor, why we are using the full network? So what is the benefit of using the subnetwork? Like we already have the full network. So how we are like mitigating the resource?
Yeah, so you will see that as I go talk about the reasoning behind it. Okay, so yeah, so as to your question, so why do we using this subnetwork, right? So why this will help the training? So I will explain this maybe step by step. So let's just look at the mutual net training paradigm, right? So how does mutual learning help the network learn better, right? So basically, all these full network and a sub-network, they share the weights, right? So basically, they're using the same set of weights. They optimize together. So you can consider this is an ensemble of networks, right? And they kind of learn together. And if you think about, right, these sub-networks, right, and they taking some of the lower resolution. And as we, in the very beginning, talk about the CNN, right? So these kind of multi-scale representation is going to be very helpful to learn the different scale representation, right? So think about if you have a smaller input size, if you're still using like 3x3 and 5x5, the receptive field size will be larger, right? Because this is a downscaled version of the CAT, right? Maybe a 3x3 region is able to capture maybe the whole region, like the ear or the eyes, right? But if you have a higher resolution, then the 3x3 may not be able to capture a specific object, like the eye, right? Maybe only a couple of pixels of the eye, right? So these different resolutions actually give you more global context, right? So, and we actually did a more detailed analysis from the gradient point of view, right? So here, I give you an example. We have a 40% network. Okay, so that means we only have the 40% of the channels of the full network. And we also have another sub-network, which is 80%. And because we are training together, right, so let's see how the gradient accumulated and back-propagated, okay? And these two sub-networks happen to taking two different resolutions, right? The 40 taking 128, and this 80% is taking 192, okay? So because these weights are shared, right, we sum the loss together. So you can see that the 40% network actually has some overlap, right? So here you have this 40% network. That's your individual gradient, right, coming from this 128 input. And you also, because we are summing the loss together, right, so the weight has to accumulate together. So this 80% network has an overlap. Is this 40% overlap, right? Because you are summing the grade loss together. So you have this grading coming from the 80% for this 40%. So that's why you have an overlap here. Is that clear? Does that make sense? Right, so you have these, all these networks, they share the weights, right? So they are summing together. So all these weights loss are summed together. So when you do the back, gradient calculation, back propagation, so these 40% network not only gets the gradient from itself, but also getting part of the gradient from another subnetwork, right, which is from 80%, the 40% of these 80% network. Okay, so that's the overlap region. And if we look at these overlap region, right, so one is coming from the network scale, okay, not only itself, but also some of the part from an 80% network, but also you are coming from two different resolutions, right? So one is looking at 128 resolution. The other is looking at 192 resolution, right? So you have this kind of multi-scale representation. So that is one from the network scale, the other is from the input scale, okay? So basically, you expose these network to different resolutions, right, and different network architectures. So they provide some complementary information to each other. So that's why they can, maybe learn something that doesn't or is not able to learn from itself. And once this network is trained, right, so we can do some dynamic inference. So basically, the network is trained. We can do some inference at the different configurations. And we can come up with this kind of configuration table, right? So you have, we can decide, okay, this is the input resolution. I have the full network. Then I can reduce the network at some, intervals, right? Maybe 5% interval to gradually reduce the network size. I can also reduce the input resolution and get accuracy, right? You can do the inference. So under this configurations, what is the accuracy I can get for this network? And you can also compute the floating point operations, right? Under this particular configuration, what is the floating point operations, right? So let's say 224 on 100%. This is the millions of flops for this particular configuration. Now, during the inference time, right? Let's say my battery is low. I cannot run at a particular flops, right? So maybe before I can run at 600 millions of flops. So you can look at this query table, right? So I can using the full network, right? And also the full resolution because my computation is under the budget, right? I have a budget of 6 millions of flops. So I look at this query table, this giving me the best accuracy. At the same time, this fits the computation budget, okay? But at a certain point, let's say I cannot afford the 6 millions of floating point, computation budget. I only have 300. So you can go to this query table and kind of look up, right? Under 300 millions of flops, what is the best configuration you can get, right? So maybe in this case, the best configuration is this one, right? So you have 39 millions of flops, and that is under 300 millions budget, and also give you the best accuracy, right? So based on this query table, you can figure out, okay, how should I change the input resolution, and how should I, kind of dial down my network width, right? To change the network width to achieve or to meet the computation budget. And one thing is that we don't have to kind of install all these different networks. So basically, again, you just simply install a trained full network like this, and during the inference time, you can adjust the network width, and you can also adjust the input resolution, right? And if you think about the network actually during the training has been exposed to different training configurations, right? Because during the training, my network has been exposed to like 30% network width. I have seen the input like a low resolution. I trained this together, right? So it's not like a totally a new setting. As we talk about in the very beginning, right? If you only train the full network at the full resolution and you just downgrade or reduce the width without any retraining, the performance will suffer. But in our mutual net training paradigm, during the training, the downsampling of the input resolution and also reduce the width has been already achieved during the training process, right? So the network has been experienced how the network has been reduced and how the input image size has been downsized, right? So in this case, we are able to maintain that accuracy. Okay, so that's the idea of the mutual net training. So we have a single network that is able to dynamically trade off between accuracy and efficiency. And we did some experiment, right? So on the ImageNet, classification, and we are testing under different, computation budget, right? So on the axis, so the horizontal axis, we have the floating point operations, right, in millions. And the vertical is the ImageNet top one accuracy, right? So as you can see that, the red line is our approach, which is we kind of trade off between input resolution and network width. And the blue line is only considering changing the network width. So they never consider about input resolution. So the input resolution is always like 224. So you can imagine, right? So for this blue curve, the only tuning knob is the network width. If we want to reduce the computation, you have to keep slim the network width to reduce the computation. But we have an extra dimension to trade off, right? That's the input. So in this case, we achieve much better performance across different computation budget, right? Especially under very low computation budget, like under 100 millions of flops. So you can see there's a big gap between, you consider both input resolution and the network's width as compared to only considering the network width, okay? And we also test using MobileNet v2 as the backbone network, and we observe a similar trend, right? So we are consistently outperform if you're just changing the network width. And we also compare this individually trained network, right? So basically we, just like the initial idea, right? So you can train a network under different configurations. And so this is exactly what we did, right? So MobileNet, we retrained the MobileNet under different configurations, right? Maybe the original resolution, the full network, or we train the MobileNet under a lower resolution, reduced network width configuration. So you have to train this network. If you have 20 configurations, basically you have to train this network 20 times under each configuration to gain that performance, right? But in our case, the mutual net is trained only once, right? We do this kind of mutual training, only train it once. So in this case, this individually trained approach will incur 7 times more training cost. And as you can see that they didn't even have better performance, right? Our mutual net is even outperform this individually trained, right? Because we have this kind of teacher-student distillation. They have this kind of collaborative training. They provide complementary information during the training with each other so they can learn better.
So when the model is deployed during the inference time, so it's kind of like already have the reduced version with it, or like during the inference times, you said that it should be trained like just once, right?
Yeah, so you basically train it once, then during inference time, you can reduce the number of channels, right? So that's the network width slimming.
Okay, so it's a parameter of the model.
Yeah, so you can take like every convolution layer, you take maybe the first 80% of the channel, or maybe taking the 50% of the channels, right, to reduce the network width. So that's the very simple way, right? You can slim the network, right? So, and we also did this on the MobileNet v2 backbone, and we also observe the similar trend. So this is a detailed analysis, right? So how the network actually is able to, trade off when the computation budget is changing, right? So here it shows you, right? So our mutual net, right? So is able to under different computation budget, how the resolution has been changed. So I think there's may not be very clear. So but we can see on this right side. All right, this is like a zoomed version of this portion. So for the US net, right? So basically only consider the network width. So only choices they have is keep reducing the network width. But for our case, right, the mutual net, which is this multicolored curve, so in the very beginning, to reduce the computation, the choice mutual net select is using reduce the network width, right? Because you can see that the red indicating the resolution, right? So 224, which is the original resolution, okay? So decide, okay, at this point, I'm only gonna using network width to reduce the computation, but at this point, if we keep reducing that, right, and you can see that it's not only may result to changing the resolution, right? So it's downgraded to 102 resolution, right? So because we have the lookup table, right? What's the best choice by tuning these two knobs, right, rather than one, right? You can see how these resolutions are changing at different computation budget. Besides classification, right, we can also do this for other tasks like the object detection and the segmentation. And we also did this COCO data set, right? So for the detection and the instant segmentation, and we have the same, result or the trend, right? So again, on these two tasks, these mutual net, by considering these two tuning factors, will have better trade-off, by just considering one. And here are some of the, like a visual result, right? So how, MutualNet is able to detect some of the small objects, right? But if you're only considering reduce the network width, you may miss some of the detection, okay? And this is the code. And besides, just working on the image, we also extend this mutual or dynamic network idea to video action recognition. So in this case, right, we are not only considering the spatial resolution, right? In this case, we can, changing the frame resolutions, but we can also kind of select which frame you don't want to use, right? Maybe not all the frames are equally important, right? Some of the frames may not contain much useful information, or maybe contain some redundant information, right? So we can reduce that, right? So you basically have another training dimension is how we can select or down select the frames. So as you can see that, right? So here, this figure shows you how spatial looks like, right? So maybe we have a smaller input resolution, but we are also selecting part of the, the frames or feature map, okay? So that's give you like the basic, idea of, this kind of dynamic network. Of course, you can also think about other trading, trade-off dimensions, right? Like previously, we also talk about quantization, right? So you may also throw in quantization as another tuning knob, right? So how I can distribute different quantization level, right, at different network stage, right? Maybe not necessarily each layer we need the full precision, right? So let's look at how we using this kind of dynamic network idea in the medical domain, right? So this is the first paper we published in ECCV 2022. So this is a dynamic, network for volumetric segmentation. So one thing we observe, right? So for these volumetric data, right? Let's using MRI as an example, right? So we have multiple slices, right, from this brain scan, okay? So as you probably notice, right, so some of the slices does not contain much information, right? So this basically containing only background, okay? And some of the slices may contain a very small portion of the ratio, the brain tissue. Because if you think about, right, so the MRI is like do the 3D scanning of a specific organ, right? So here is the human brain. So maybe this is like a very surface region, right? So you only get a very small tissue, right? Because the depth is not that deep. So we can actually see there's some easy slices, or there may be some hard slices, right? So the hard slice may look like this, right? So you have a full cross section of the brain, and you have multiple classes of these kind of tumor classes, right? So these different colors indicating different tumor type, right? So for this particular data set, which is from the Brett's data set from the brain tumor segmentation, we have 4 different classes, right? You have a tumor core, enhanced tumor, some other types tumors. So this is like a more complicated cases or slices, right? Because you have, all these different classes. But for some of the slices, maybe you can consider this is like a medium difficulty, medium level of slice. Maybe you only have one specific class, right? So the question or the motivation is that, is it really necessary to run a heavy network, right, across all these different slices? Right, as a human, right, when we see this kind of slice, we notice there's all background. So we don't even have to run any of the deep learning algorithm, right? So basically we can predict there's nothing, right? So you can output a feature segmentation map with all zeros, right? Because we know basically these are all background, okay? And for some of the easy class, maybe this slice, right, so only have a small region, right? So maybe you don't have to run the network through the entire slice, right? Maybe you can focus on the small region and even using a smaller network, right? Because this is a very easy case. You don't need a very complex or heavy network to get a very confident prediction. Maybe a lightweight network, a smaller network is able to give you a very confident prediction, right? So we want to, based on the characteristics of your input, and to figure out how we can intelligently distribute the computation, right? So basically, the high-level idea is that for some of the easy slices, we can maybe totally doing a skip, right? Don't run any of the network, just predict output, maybe total or all zero, right? And for some of the easy or medium slices, we run a lightweight network, and we are able to generate maybe a confident prediction. Only for those slices that is very complex, right? With all these different textures, then we run the most complex model, right, to generate a prediction. Okay, so the idea is that we want to achieve this kind of dynamic inference with adjustable network structure. Okay, so here to achieve this goal, we basically have to come up some sort of a decision mechanism, right? How do you determine, right? This is a easy slice. This is like a medium level slice, or this is like a complex or hard cases, right? So what we do is we kind of design a decision network, right? You can also maybe call this like a policy network. So basically, can be a very simple network, like a couple of CN layers, or maybe only MLP layers, right? So the job is not to do pixel-wise segmentation. The job for this decision network is to give you an idea, right? So to output, is this as an easy slice? Is this as a difficult slice? Or this is like a medium level slice? So basically, we can specify like maybe 3 or 4 classes, right? So here we have like a skip, 0, right? The class is skip, which means you don't run any of the prediction model, just output a segmentation map of 0. And we also have a decision 1 to maybe to n, right? So this can be indicating different levels of difficulty, right? So this is maybe a little bit, one can be considered like an easy sample, right? So for this easy samples, or this level of easy samples, you can run a lightweight network, okay? So basically, for each of the difficulty level, we assign a specific candidate network, right? So you have this M1 to Mn, right? So basically, they have different network architectures or complexities. So here, basically, M to Mn, you have a more complex network, okay? Yeah, so here, this is basically like illustration, right? So for these different candidate network, we have using 2D UNet as the backbone network. But what we can do is using this kind of slimmable network idea we talked about before, right? Using different network width, right? So the smallest one maybe only have like 20% of network width in that UNet structure. But the last candidate model, which we consider the heaviest model, we will have the original 2D UNet with all the channels. Okay, so basically these corresponding to different complexity or difficulties. So now what we do is we have this kind of a 2 network, right? So you have a lightweight decision network to decide which level that is for particular input slice. So based on that decision, right? So this is like a circuit, gate, right? So which one we connect to, right? So based on the decision, okay, this may be output a skip, right? Class 0. Then we connect to this branch, and without any of the prediction model, we generate the prediction. And maybe the next slice, this decision network give you a decision of maybe class 5, right? So we connect with candidate model 5, then using that model, right, to make a prediction, okay? Of course, the decision network has also been trained, right? Because in the very beginning, this network doesn't know, right, which one is the best, right? Which model you should use. So here we have like a joint training, basically. You have this class, segmentation, right? We're using the Dice loss, right? You compare with the ground truth. You have the Dice loss. And you also have computation, right? So because right now we are considering accuracy and the computation trade-off, right? So you want to also have the computation as another objective function in the optimization, right? So you have the Dice loss, and you also have the G flops, right, as your computation objective, and using them to jointly as your training objective. So these G flops actually coming from how the decision network is making the decision, right? So that's why these G flops is also able to affect how the decision network is able to gradually make reasonable decisions that you do not suffer from accuracy drop a lot, but at the same time, you intelligently select the best candidate network to achieve the best efficiency as well. Okay. So here are some of the the loss functions we use, right? So for how the decision network is trained, but basically is what I just mentioned, right? So we not only considering the Dice segmentation loss, but we also considering the floating point operation, right? Basically the computation budget. Okay. So once the network is trained, then we can using this kind of dynamic network to do the inference, right? Based on the slice, we can select which network to use. So here, one thing I should mention that because of this mechanism, right, we cannot do volumetric segmentation. So we basically do slice by slice segmentation, right? Treating each slice as independent to the image and run through this decision network or policy network and determine which network we want to use and do the prediction. Okay, so we do this slice by slice. So for the performance evaluation, so we are not only care about the overall segmentation accuracy, right? So we're using the Dice score and also the Hausdorff distance, right, as the common metric to measure the accuracy. But we also care about the computation, right, complexity. So we're using the flops to measure the complexity as well. So as you can see that the accuracy actually is pretty good, right? So for the Dice score, right, this enhanced tumor class, we are able to achieve the best accuracy as compared to all these different networks. So some are involving 3D networks, and some of them are using like a hybrid network using transformer and CN architectures. And one thing to notice is the floating point count, right? The flops count. So we are able to achieve significant reduction, right? So if you look at the 3D unit, right, the first row in this table, the unit is for each of the case, right? Case means all the 3D MRI as a whole, right? So it has 1,700 G flops, but for our case, we reduced about 20 or 30 times, right? 25 times, around 20 times. So for the case, we only have 78 G flops. And we can also consider how another case is per slice computation, right? If you compute the flops, right, for each of the slice, how much you have to take to compute the segmentation for each slice. For the 3D unit has 13 G per slice, but in our case, we only have less than 1 G flops per slice. So it give you much efficient computation, right? So if we consider this kind of dynamic architecture. And we also do the visual comparison, right? So show the segmentation map, right, with different segmentation networks, and right, compare the ground truth, right? So our is also have better segmentation accuracy, right, compared to attention unit, 3D unit. And this is another data set, right? So for the liver tumor segmentation, right? So we are using these CT scans, right? So again, so we are perform much better in terms of the computation, right? Because we are effectively considering the computation as another optimization objective. And here we basically trying to get some analysis, right? So how these decision network is making the decision, right? So here, as you can see that from this MRI data set, when we do some statistics, right? How many times the decision network is making a prediction you should skip, right? Actually, we see like 60% the cases we're actually using a decision of skip, right? So that's where a majority of the computation reduction come from, because you have like 65%, you are not running any of the network, right? So you basically just skip any of the prediction model, just predict the output. Maybe because of these network doesn't produce much information, or we know at this kind of tissue may look at all normal. There's no brain tumor in it, right? So we can confidently predict they all corresponding to the normal class or background. And we have like 10%, around 10% using the M1 model. So M1 indicating this is a very lightweight, maybe only have like 10 or 20% network width of the unit, right? So this is very lightweight, and we have 10% of such slices using these M1 model, okay? And we only have like less than 4% of the slices actually has to require to run the heaviest model, right? M4 corresponding to the most complex model, right? So only for this kind of complex slices, right? So you can see all the tumor classes are there, right? So a lot of boundaries we have to be consider to do not over segment or under segment, right? So you want to have a very complex or heavy model to make very accurate predictions, but only like 4% of them you have to go with this very heavy XMR model to achieve very good segmentation. So based on these kind of analysis, we kind of have an idea, right? So how the majority of the reduction come from, and how we can distribute the computation across different slices based on their characteristics. Okay, so that's one work. So actually the first work we have done, right? So for this kind of dynamic network for MI segmentation, right? As I mentioned earlier, in the hospital healthcare setting, computation maybe is not always be available, so it's kind of a scale resource. So we can actually from the algorithm side, right, to determine how you can intelligently use your computation available, okay? All right, so based on the idea I just described, right, the mutual net, I want you to think about, right, any ideas, can we further improve these meta-DA net, right, this dynamic network to improve the accuracy or efficiency for medical segmentation?
For the mutual net, you say that we're using white, we're reducing the white, right? But we said that we can also do some another quantization techniques. So for that, we can also use that type of technique rather than reducing just white of the network.
Yep.
Other techniques like quantization or.
Yep. Exactly. So yeah, kind of our idea kind of converged to the same point. So that's why we have our follow-up work. So we come up with meta-DNet V2, right? So this is published in WACV 2024. So we further improve, based upon this idea, right? So the previous one is kind of very, just like a proof of concept, right? So if this kind of dynamic network is able to achieve very good trade-off, but now we want to come up with maybe more, a better idea or consider more factors, right? So how we are able to further, have a better efficiency and accuracy trade-off. So one thing we notice is that, even though we are able to make some decisions, right? So which network can we totally skip this slice, or we can using a light network to run the prediction, but we never consider the region of interest, right? So even for this one, the more complex slices, we can see that there's also a majority of the region corresponding to background. So this is some of the inherent thing with how the imaging sensor, right? So these MI scans will generate image that has a certain resolution, but the region of interest only occupy maybe the center, right? So, but as we design the algorithm, we want to take into that as into account as well, right? So in this case, we go further, right? Not just consider the entire slice, but we also considering the region of interest, right? So in the mutual net, we do the downscaling, but in this case, downscaling is not a good idea because downsample the original medical image, maybe you lose some of the important information, right? So, but for the medical image, accuracy is really important. So in this case, we resort to cropping. Okay, so which specific region we want to crop out as the region of interest, and we only run the network on that region of interest, right? So the region of interest may not be like, you can put like a threshold or something like that, trying to crop out the entire region, right? Like the brain shape. The region of interest we are talking about is maybe we can also cut off some of the normal tissues here, right? So if we are confident about these regions are corresponding to normal tissue, then we can basically predict output, right? Because after all, we only care about a very accurate delineation of this tumor region, right? So if we were confident about some of the normal tissue region, then we may not necessarily have to run the output run the prediction model there, right? So I don't know if you can see this here. Actually, when you look at this, right? So some of the regions, or maybe I can using this pen to kind of crop out, right? So these part, right? These very small part actually corresponding to some normal regions, and we are considering we don't have to run the network. So only this black one. So it's like the crop out region. Okay. So we run the network. So here is something we have to use in the policy network, right, to determine, maybe the center of this bounding box and also the height and the width of this bounding box, right, where you want to crop. And so that's another kind of, reduce the spatial redundancy, right, to reduce the, computation from the data input. And the second is we also considering not only slimming the network width, but we also considering the quantization, right? So at different stage, right, the UNet have different convolution layers. Can we dynamically distribute the precision into different layers, right? So maybe in this stage, I'm using 32-bit, right? So for the next stage, maybe I will using so this is like the fixed full precision network. But for our dynamic, right, so maybe this one is 16-bit, this one is 18-bit, and for some of the layers, maybe we have a higher or even lower. So that's another trade-off dimension we want to use, which is the quantization level. Okay. So just putting everything together, right? So you can see the diagram become more complex, right? So here, for this policy network, we want to decide, right? So are we going to totally skip this image, or are we going to using the entire image for the prediction, or we have to using crop size, right? And what is the crop size we want to use, right? So basically, we want to determine, right, the crop center and also the height and width of the bounding box. So eventually, then we can reach a region of interest, and then we can using that to feed into the later network, right? To decide how you can distribute the computation, either from the width point of view, also from the quantization point of view, right? So how we are able to achieve this kind of dynamic inference. Okay. So if you look at the overall architecture, right, so the loss function, so you have the dice loss, right, so that's corresponding to the accuracy. So we definitely care about the accuracy. And second is we also care about the, the flops, right? So this is affect the policy network, right? Because, if you have a tight budget, right? So maybe this affect the policy network, how you are making decision, right? So we using these two type of loss to in the joint optimization, hopefully, this policy network or decision network is able to make a better decision to achieve the optimal trade-off between accuracy and efficiency. Okay, so I didn't put the result here, but in our paper we compared to our V1 model, so we are also able to achieve much better, efficiency as well as doesn't suffer from the accuracy drop. So yeah, it's intuitive to understand, right? So because we are also able to reduce the input size, the regions, and we are also using quantization, as another trade-off dimension. So definitely we are able to achieve much better efficiency. So if you are interested in this kind of dynamic network, so I listed a couple of references, and also some of the efficient network, like in terms of pruning and quantization, so you can take a look. If you want to know more details, so all these, the papers has all the details, and the code is also available. So you can think about, if there's anything more you can do, right, to achieve, better efficiency. And so I think that will be a very interesting direction, right? So I think if you heard of DeepSeek, right, so the way they are able to using a low-end GPUs to train a such good large model is they also using this kind of 8-bit precision to train that model, right? So that's where they can, kind of compress that model or make it more training more efficient. So I think efficiency is become more and more important, right? Because as we scale up the model and scale up the training in terms of data set, we cannot, at least if we are not a big tech company, so at least in the academia, right? So we have to care about efficiency, or maybe some applications, right? Efficiency are really important, right? So I think this is a really, interest directions. Hopefully, you guys find this interesting as well. So maybe if there's any potential idea, right, to further improve that, I'll be happy to discuss with you, right? So I think this could also be something really interesting if you want to do some project based on that, right? So I think there's definitely other things we can consider to maybe further make this model more efficient, right? So here we still kind of like a very coarse design, right? So here maybe you can think about, can we using some like edge detection or some lightweight network to figure out, or saliency map or something like that, to figure out what are the important region you want to use. So yeah, I think there's more maybe we can do. So hopefully, so you may have ideas. We're happy to discuss with you. Okay. Okay, so I think that's all for today. So for the dynamic network, so you hopefully find interesting. Any questions before we end? Okay, all right. So if you don't have any questions, we can end here. So I will talk to you next week.